to try and translate this graph. So Peter said you're going to take the y values and you're going to multiply them by 2. Because in a function, f of x and y are interchangeable. So if it says take 2 times f of x, well, that's really the same thing as saying take 2 times your y variable. So if I take my y variable and those numbers and I multiply each one of those by 2, I then have a new set of ordered pairs. So I would have a 0 with a -2. That's going to be my new point of this graph that I'm transforming. I would have 1 with 0. 3 is now with +2, and 4 is with +4. My x's aren't changing because there isn't anything inside the function f of x. There's nothing inside the parentheses with x to change the x variable. So when we go to make this new graph, Peter said multiply the y values by 2, which I did, and then we're going to plot these new ordered pairs. So these 4 ordered pairs, we're going to graph them. And then I should hopefully see that this graph has a vertical stretch. So taking my ordered pairs, it now goes down to -2 instead of being at -1. It's still at 1, 0, because if I take 0 times 2 or 0 times anything, it's going to stay the same. My point at 3, 2 is now up, or 3, 1 is now up to 3, 2. And then I had a point at 4, 2. Well, that's now up at 4, 4. So when I connect these points, I want to connect them in the same form that they were connected before, because the shape shouldn't change. So I still have a line connecting the first 2 points. And then I have another line with a different steepness, and then I have a final line with a different steepness. That middle one looks crappy. Yeah. But I can see that vertically, as Jack said, it's a vertical stretch. So my original graph is shorter than my new graph. The new graph is being pulled vertically. And that's because the number in front is changing y. Anything that changes y stretches our graph or does something with the graph vertically. So again, I just listed ordered pairs. I took the y value of those ordered pairs and I multiplied them by 2 to get a new graph. I apologize that my graph doesn't look so good. That middle line there connecting those second and third points, just not happening for me today on the iPad, I suppose. Any questions with number 19? So number 19 was a 3-part question. Part A and C were shifting the graph. Part E was the one that stretched the graph, kind of changed the steepness of that graph. Any questions? The other one that I wanted to just look at was number 45. I think it was questions 23 to 45 that you had to do odd, and that just relied on looking at the equation and describing what was happening with the equation. And number 45 gave you the equation y equals the square root of 4x. Before you describe this transformation, can this equation be simplified? Darby, could I simplify this equation at all if I have y equals the square root of 4x?
Yeah, you can square root 4, so it'll be 2 square root x.
Yeah, and that's a property of radicals. So it's called the product property. I could separate them and just look at the square root of 4 and the square root of x individually. They're still being multiplied, but I'm allowed to separate them into their own individual radicals. So product property of radicals.
Miss Kane.
Yes.
Joe got kicked out of the Zoom.
Oh, thank you. Thanks for telling me. I have that like pushed to the side. Thank you. Sorry, Joe. I'm sorry if you were waiting for a while. Peter helped you.
It's okay.
I kind of have my participant list kicked to the side. I didn't notice that you got kicked out. I apologize. Thanks, Peter. All right, so this is our new equation for 45. Now we have y equals 2 and then the square root of x. Darby, what would this transformation become if there's a 2 now in front of the square root of x?
It would stretch and it would be similar to what we did on the number 19 problem.
Yeah,
Because you would just have to multiply the parent function by 2.
nice job. Good explanation. So once we simplify it, it becomes 2 root x, while that 2 is being multiplied by our function or the y values in the function, so that's going to stretch our graph. So anytime the number is bigger than 1, it pulls the graph vertically. And we're going to look at one more pair of graphs to show like that vertical stretch in the graph. Does anyone have questions? So as I said, we're going to do 2 more graphs, and then we're just going to look and like analyze functions to make sure everybody feels comfortable about stretching, shrinking, shifting, reflecting equations, and what the notation is telling us. So in your packet, looking at page 18, just kind of do a little summary here, wrapping up these transformations, kind of generally thinking about what's happening. Example 5, we're back to our favorite graph, y equals x squared or f of x equals x squared. So I'm going to graph that just to remind us, we know it's a parabola, but just to have a basic graph drawn, the parent function. All right, so we have y equals x squared, or f of x equals x squared. So if I look at g of x, there's a 5, and then in parentheses, it says x minus 2 quantity squared. What's going to happen to this graph? So thinking about the 2 that we just looked at, what happens with this graph? Ethan, what do you think happens with this graph? What's the like inside part, the x minus 2, how's that going to change it? How does the 5 in front change it? Do you know one of those 2 parts, Ethan? Brenna, could you help him out? What do you think? What's going on with this graph? What kind of transformation do we have?
Wouldn't it be a vertical stretch and translate 2 to the right?
Yeah, nice job. So the number in front's bigger than 1, so vertical stretch. And then the part inside, yes, it says x minus, but remember the minus is part of the general equation. That's standard way we write it. So it's really moving to the right too, shifting right too. All right, so we're going to see if we can apply that and make this new graph. So we know it shifts to the right too. And then the 5 is a vertical stretch. So if I look at my original point, I went over 1 and 1 squared was 1. But now if I go over 1, 1 squared is still 1, but that 5 stretches my graph. And instead of going up to 1, I have to go up to 5. Because I need to multiply my y value by 5. So if it was originally a y value of 1, now it's being multiplied by 5 and it's stretching vertically. So again, on the other side, if I had a y value of 1, that y value stretches vertically and becomes a value of 5. That's what the number in front does. So it multiplies y by 5. Now, my other y value is up at 4. If I multiply 4 by 5, I'd have 20. Then I don't have room on my graph. But I can at least connect these 3 points and see that I have a vertical stretch in the graph. It shifted right, but also it became more narrow. It stretched vertically. And that's what that number in front does. So it takes the y values and multiplies it by 5. Questions? So there's one more problem right next to it, just kind of using the same numbers, but showing you the location being a little different in that -2 and how that changes the graph. So Caden, what's going to happen with h of x equals 5x squared minus 2?
It's gonna stretch and go left 2
Where
or
is
right 2.
where is the -2, like in relation to, if you look at the first one versus the second, where's that -2 at?
Would it go down 2?
It does go down 2, and that's because it's separate from x. It's not grouped in parentheses. So when the number is in parentheses with x, it affects the x. If there aren't parentheses, that -2 is like separate from the x value, and it's affecting the y. So if it's not squished in parentheses with x, then it has to affect the y of the graph. So this goes down 2. So looking at my original graph that I had drawn, that parent function, it's going down 2. And then I still have to do the same other steps. So typically I would go over 1, up 1, but that y value is still being multiplied by 5. So from where my new vertex is, I need to go up 5 units. Again, if I go over 1, 1 squared is 1. So normally my y value is 1, but now I need to stretch up 5 units from that initial vertex value. And that's because of the number in front. I need to multiply the y value by 5. So it's stretching my graph. Any questions? So you can see the difference in the location of the -2 and what it does to the graph. When it's with x,
So do we,
left or right. Darby, question.
sorry about that. Do we have to always, like, do we have to graph the parent function like every time? Or like, cause like you didn't graph it on this one?
No, you do not have to graph it every time. No,
Okay.
especially if it's the same equation. So graph it once, use that one graph, and then you can kind of just compare to the initial graph. Good question. But no, you don't have to graph it every time. You've got a graph right next door. Other questions? So if I'm looking at the shape of the graphs for part 1 versus part 2, they have that same vertical stretch. That part didn't change. Just the location of the graph changed because it shifted down instead of right. All right, so the last part of this, and this should be really quick here, we're just going to kind of describe what happens to the graph. And I think there was a question or two like this in your homework, and it wasn't meant to be confusing. So it says, given the function x cubed plus 2x. So here's our function. What happens to the graph of the following? It doesn't matter what the function is. My equation could be huge. I could have x to the 6 plus 2x squared plus 5x plus 4. The way the expression is written or the function notation is written really describes what's happening to the graph. So the little f in front is function notation saying refer to your given function. But this x plus 2 is the part that's going to tell us what happens to the graph. It doesn't matter that our function says x cubed plus 2x. So this is that general information that we talked about yesterday. So yesterday we said in general, trying to find it right here. For any function, if I have x plus c, no matter what the function is, it's going to move to the left. So that's what this question is kind of asking us. What is going to happen to this function in general? So in this case, since it says x plus 2, this graph is going to shift left. Again, it doesn't matter what the function is. It's the notation that we're relying on. X plus 2 is really x minus and then a -2. So it's moving to the left because of the -2. That's all I have to do, describe what happens to the graph. So letter B says 2 and then f of x. So what would happen to the graph if it had 2 times f of x? Joe, what's going to happen with that graph if it says 2 f of x?
It would be a vertical stretch.
Nice. And that is applied to any function, whether it says x cubed plus 2x or some other crazy function. If it says take 2 times f of x or 5 times f of x, it's a vertical stretch. Letter C says f of negative x. All right, gotta think, what is that negative sign doing in there? How does that affect the graph? Hannah, do you know what that negative sign with x does to the graph?
It's gonna flip it over the y-axis.
Awesome, nice job. And it flips it over the y because the x values are becoming negative. So here's my y-axis. Well, x is positive, but now I need to make it negative. And in order to do that, I have to hop over the y-axis. The next group of problems are asking you to do the same thing, except it's saying we have this equation y equals x to the 4th, and it puts it back into equation notation. So there's function notation when it just uses an f of x. There's equation notation when it actually applies the change to the equation. But they both do the same thing. It's just writing it in function notation versus writing it as an equation. They mean the same thing. So see if you can, for these 4 problems, write the change that would take place. What transformation is happening? So describe the transformation, A through D. All right, Jenny, do you have letter A?
It would move it to the right 2 units.
Nice. And Jenny, how about letter B?
It would be a reflection over the x-axis, and then it would move up 3.
Good. So it's reflecting over the x-axis because the y's are becoming negative. So when you have the negative in front of the x to the 4th, that's our function. Our function's becoming negative. A function is the same thing as y. So reflecting over the x, and then she said up 3. And you can see the difference. Like if it's in parentheses, it's connected to x. If there aren't parentheses, it's not changing x. Jack, how about letter C? What's going on with letter C?
It's a vertical stretch and down 5.
Good. Again, no parentheses, so we're changing y. It's affecting the y variable. And then Jack, how about letter D?
A reflection over the x-axis, right 2 and up 1.
Nice job. It's moving right because inside with x, it says x minus, that's part of the equation, and then there's a 2. And then outside, it's going up 1. Does anyone have questions with those 4 problems?
What's the difference between like reflecting versus like flipping over the y-axis? Like,
Same
does that
thing.
just depend on the, okay.
Yep, so you could say flip, you could say reflect, you could say mirror. They all mean the same thing. So flip
Okay.
over the x is the same thing as reflecting over the x. Just a different term you could use. Other questions? Good. All right, so the last group of examples, this is it here. This is a little weird. It says let f of x equal x cubed. So our f function is x cubed. The g function is the square root of x. It wants us to express the transformation, or express each as a transformation of f or g. So essentially, it wants us to take the equation form, which is what we had in example 7, and change it to function form, which is in example 6. As I said, there's two different ways that you can kind of write a transformation. You can write it with function notation, or you can write it as an equation. So this question is kind of telling us to take it out of equation form and write it using function notation. So if you look at A, we have y equals the quantity x minus 4 cubed. So let's just start. Jeremy, what function would this be talking about? Is this the f function or the g function?
The f function.
Because,
It has the cubed.
right, it has the cubed in it. So I'm going to take and use the function f. And then Jeremy, if I was graphing this, what would happen to the graph? What kind of translation would this be?
Shifted left 4 units.
Close, not
Maybe
left.
right.
Right. It would shift right 4 units because we're changing the x. So when we go to write this in function notation, I'm using the function f, but I'm still writing it as x minus 4 to show that it's moving right 4 units. The only difference is I'm not saying that's cubed anymore, because if I use the function f, it's implying that my function or my x is cubed. So I have the equation, but now it's written in function notation. Questions? So using the function f implies that I have an equation that's cubed. This graph is still shifting right 4 units, whether it's in equation form or function form. So letter B, we have y equals the square root of x and then plus 7. Peter, how do you think this equation would transform to a function?
I had g of x plus 7
And where do you have the plus 7 at?
outside the parentheses.
Excellent. And it's outside because?
It's not under the square root.
Perfect. Very nice. So g of x function, because it's a square root. The plus 7 is outside the parentheses because it's not underneath the square root. So if we look at letter C, we have 2 times the quantity x plus 3 cubed minus 1. Olivia, do you think you could try and write this as a function?
One second. Would it be f of x and then would that be cubed?
So you're using the f, so that means it is cubed, so I don't have to worry about the cube part.
Oh, okay.
But what's inside with x?
The 3, so it
Right.
would be plus 3.
Plus 3. And then what's outside of?
And then it would be minus 1.
Yep. And then in front, there was a 2, so there's still a 2 in front.
Okay.
So like the equation doesn't really change the function. The only part is we're not including the cube anymore because we're using the function f. But if you like comparing the two, they look identical. It's just it's not cubed anymore. So when we go to look at letter D, I still have a 6, I still have a minus. Instead of using the square root, I would use the function g. Underneath the square root is x minus 2. So that means it's with x, in parentheses, it has to be x minus 2. But again, if I compare the two, they look almost identical. It's just I don't have that square root in it anymore. We have the function notation for g. So in general, if it's attached to x in parentheses, when you write it as a function, it needs to remain in parentheses with x. If it's outside of the actual part that's being cubed, then it should remain outside of the function. Does anyone have questions? So I just want to show you your worksheet, just so that you kind of get an idea as to what you're looking at. I actually posted this worksheet separate on Google Classroom, and I put a graph with each one of them. So it's up to you if you want to use the worksheet that's in the packet, or if you want to use the worksheet that's on Google Classroom. But again, the worksheet on Google Classroom has a graph right next to f of x plus 3. So the directions for this problem say the graph is shown of y equals f of x. So this is a piecewise function. It's drawn from the interval of -2 to +2. That just lets you know that it doesn't go beyond those values. So it stops at -2, it stops at +2. On graph paper, or if you use the one attached to Google Classroom, doesn't matter because you could use Notability for this as well. Graph each of the following problems using the original graph that's shown. Label your graph, or I would suggest just making a T-chart of your graph and writing the new ordered pairs. So you're going to take a couple of points on this graph, and I would just take the points where it changes direction. So I have a point at -2, 0 on the x-axis, a point at 0, 3, a point at 1, 2, and a point at 2, 2. Those are the ordered pairs that go along with my original graph. You are going to transform this graph based off of what the 6 problems are asking you to do. So if you look at number 1, Peter, what is number 1's notation telling you to do with the graph?
Shift it to the left 3.
Right. So Peter, if we're shifting to the left 3, what does that mean you're going to do with your x values?
You're gonna subtract 3 from them.
Exactly. So you're going to take these original values for x, you're going to subtract 3 from each of the original values. So I had -2, I'm at -5. I had 0, now we're at -3. We have 1, now we're at -2. We had 2, now we're at -1. So we're taking these values and subtracting 3, because that's what it means to move left on a graph. It means to subtract 3 from x. But the y values aren't changing because we're not doing anything with y. We're just shifting the graph left. And then I would plot those new ordered pairs. And when I graph them, you should see compared to the original graph. And no, as Darby said, do we have to graph the original one every time? No, it's given for you there. But you should be able to see the shift of this graph compared to the original graph. My x values have moved to the left. So you're going to do that for those 6 problems. And then underneath, this is like the 4 problems we just went over. You're going to change it from equation notation and write it as a function. So you're graphing 6 problems, and then you're just rewriting these equations using functions. And that's it for your homework. So again, the one that's attached to the assignment in Google Classroom has graphs attached to each problem. So you can choose to use that one, or you can just choose to do this on a slide of graph paper and Notability and just make your own graphs there. Or just do it on a separate piece of paper because you have graph paper that's regular paper at home. Totally up to you. Tomorrow, I have that little video that explains some of these problems and explains a little bit more about transformations. And then there is a second worksheet like this that you're going to do for tomorrow. Does anyone have questions? So have a great day. Thank you so much for being fantastic over the last 5 weeks. I am truly excited to see half of you on Monday and Tuesday, the other half Thursday, Friday. But thanks for being awesome over these last 5 weeks. I truly appreciate all of your hard work. So have a good one. Thank you.
Thank you.
Thank you. Have a good
Thank
day.
Bye, Miss
See you
King.
later.